and as without your support, this conference wouldn't have happened. Thank you so much. Now, for today's session, we also have keynote speeches. Now, I will kindly ask our distinguished guests take a seat so you would have a chance to observe demonstration of our keynote speaker. Please. For now, I would like to invite our honorable, well-known professor on stage to deliver his keynote speech, Doctor of Technical Sciences, Professor at the Department of Artificial Intelligence of TUIT University, Professor Musaif Muhammadjan, speaking on the topic of Uzbek speech processing. Please welcome our professor on stage. It would really help us delve deeper into the subject and understand its nuances, please.
Займемся делом. Название моего доклада «Развитие речевых технологий в Узбекистане».
The theme of my topic is developing speech processing technologies in Uzbekistan. So professor will explain in Russian. So I'll try to translate it into English. I'm also his student.
Итак, тут много говорилось о дружественном отношении к компьютерам, об интерфейсе. Мой сегодняшний доклад посвящен тому, что в нашем университете реализуются проекты, которые прямиком направлены на повышение дружественности по отношению к компьютерам и развитие интеллектуального интерфейса.
Before my speech, there was too many words about human-computer interaction. My topic is dedicated to the development of speech technologies in Uzbekistan. It also is a part of the human-computer interaction.
Базовыми составляющими интеллектуального интерфейса являются речевые технологии, анализ и синтез речи. Поэтому автоматическое распознавание речи является динамично развивающимся направлением в области искусственного интеллекта.
The main part of the human-computer interaction is the speech processing, which consists from analysis and synthesis, and so that it's mainly part of the human-computer interaction.
В целом, исследования по проблемам искусственного интеллекта ведутся во многих институтах и университетах Узбекистана.
In common, and in the direction of the speech processing are developed in so many universities.
Это Институт проблем математики Академии наук Республики Узбекистан, Национальный университет, Государственный технический университет, Самаркандский государственный университет.
There are institutes of mathematics and of the Academy of Science of the Republic of Uzbekistan, National University, and State Technical University, and Samarkand State National University.
В рамках исследований по искусственному интеллекту и речевым технологиям занимаются ученые нашего университета, Ташкентского университета информационных технологий, Национального университета и Института развития цифровых технологий нашей республики.
With the speech technologies, going to research in Tashkent University of Information Technology, is a national university. Also, in the Institute of the Development of Digital Technologies.
Я немножко хотел бы рассказать вообще о развитии речевых технологий в мире.
I'm also, before starting, I'm going to talk about the short history about the speech technologies in the world.
Первые технологии в 80-е годы развивались в Соединенных Штатах. Были созданы первые системы распознавания изолированных цифр. Была создана программа идентификации диктора и распознавания отдельных слов.
The first speech technology with speech technologies got research in USA, especially in 18th or 21st century. They start processing and recognition of the numbers and the dictor identification.
90-е и 2000-е годы пришло понятие машинного обучения, использование технологий анализа больших данных. Появились системы автоматического построения алгоритмов обработки языка, Natural Language Processing, внедрение систем синтеза речи в компьютерах Apple и появление первых коммерческих систем машинного перевода.
From starting 1990, it came to speech processing is machine learning, and after that start doing the natural language processing also.
С ростом вычислительных мощностей компьютеров в 2010-е годы появилось направление алгоритмов глубокого обучения и набирает силу и популярность сквозная технология TUIT, где все промежуточные стадии обработки языка делаются с помощью глубоких нейронных сетей. Они формируют автоматически, ответы формируются автоматически с одновременным улучшением качества результата.
In 2010s, learning algorithm based on the deep neural networks transition to end-to-end solution of speech recognition problems. They start recognize the whole words.
В настоящее время, значит, уровень работ по развитию речевых технологий достиг машинного перевода и по качеству своему приближается к естественной человеческой речи.
Nowadays, the speech technologies grows up and transition to multilingual speech technologies and approach it in the human level is speech analysis and synthesis, and they nearly became as a natural language.
Теперь я хотел бы перейти непосредственно к проекту, который реализуется в нашем университете при финансовой поддержке Министерства инновационного развития. Вот, он посвящен созданию, значит, программ анализа и синтеза речи для государственных органов.
Now I'm going to talk about the project, a local project doing with our university and Ministry of Innovation. I'm going to talk about this project.
Значит, теперь первый этап, я говорю на первом этапе про программы распознавания или анализа речи. Об этом пойдет речь.
First, I'm going to talk about the analysis of the speech, especially recognition. It's the first part of our project.
То есть речь пойдет о технологии речь-текст.
We will be talk about the speech to text technology.
Такие технологии используются в колл-центрах, в составлении государственных протоколов, журналистике, медицинской диагностике, в образовании и при изучении иностранных языков.
This kind of technology is uses in call centers, also in healthcare, in education, and some part of medicine.
В таблице представлены требования
In this
в
table,
соответствии с которыми мы разрабатываем свои технологии автоматического распознавания узбекской речи. Я должен сказать, что во многих странах, прежде всего в английской речевой технологии, и в Германии, и в других западных странах уже существуют программы, которые автоматически переводят, транслируют, значит, речь в текст.
I'm going to say that in modern countries like Europe, in America, also India, already there has our own speech recognition technologies. In this table, I'm going to show the steps of these speech processing technologies.
Для узбекского языка этого сделано не было. Мы начали свою работу несколько лет назад, и в настоящее время получили первые результаты, вот, о которых я хотел бы вам сообщить.
In Uzbek speech recognition, before no one did this kind of technologies, and they were not this kind of technology. We start doing this research, and we have some results. We start maybe 10 years ago, and we have some results. I will discuss about my results.
В данной таблице представлены требования, в соответствии с которыми мы реализовали свой проект.
In this table, shown the levels of which we develop our system.
Значит, первое, тип анализируемой речи может быть распознавание отдельных слов, распознавание сочетаний слов и распознавание непрерывной речи. Красным выделен тот, за что мы взялись. То есть мы взялись за распознавание непрерывной слитной речи в реальном масштабе времени.
First, here is a type of speech recognition analyze technologies. Here is with red color, which we're going to do. They are, first is word recognition, second word combinations recognition, last one is a continuous speech recognition. We are doing research in continuous speech recognition of Uzbek language.
Вторая таблица, второй столбец показывает зависимость от диктора. Возможные варианты распознавания, зависимые от диктора. Есть вариант настройка на конкретного диктора. Есть распознавание независимое от диктора. То есть независимо от того, кто бы ни говорил, значит, его речь транслируется в текст. Мы выбрали нижний вариант.
Second column is dictor dependency. It means that first is dictor dependent system, and second is adjustable dictor independent system. Last one is totally dictor independent system.
Третий столбец – это объем речевого словаря, то есть насколько слов он рассчитан. Есть варианты с ограниченным словарем, есть со словарем большого объема и со словарем без ограничений. У нас вариант реализован для словаря без ограничений. То есть мы никаких не ограничиваем, что он должен говорить. Он говорит все, что хочет.
Third column is the volume of the speech dictionary, word dictionary. So is first is a limited words recognition with limited words, and second is recognition dictionary with large dictionaries, and the last one is with no limitation in dictionary.
И последний столбец – это выбираемые технологии обработки. Есть варианты, существуют в мире варианты на основе марковских цепей, существуют варианты на основе простых, значит, нейронных цепей. И вот выбранная нами технология, она основана на глубоких нейронных сетях по технологии end-to-end.
The last column is technologies where developed speech recognition. In here is the first two is based on the hidden Markov models, and second is based on hidden Markov model plus artificial neural network. It's some kind of hybrid technology. And the last one is the end-to-end technology, which is we are using in our projects.
Я хотел бы рассмотреть процесс создания программы автоматического распознавания речи и почему мы называем его технологией, потому что в этих мы не говорим о том, что это отдельный алгоритм, мы говорим, что это целая технология, потому что есть этап создания, есть этап создания речевого корпуса, этап выделения информативных признаков речевого сигнала, есть этап проектирования акустической речевой модели языка распознавания, то есть узбекского языка, есть этап разработки нейросетевой архитектуры и распознавания речи и этап создания модулей автоматического распознавания речи. Мы считаем, что вот это все можно назвать технологией.
You may ask why we don't use algorithms or stage. We are using the technologies because the whole process of creating automatic speech recognition system is completely technology for preparation and processing information, and includes the following main steps. First is a creation of speech corpus. Second, selection of informative features of speech signals. Last is designing acoustic and speech models of the recognition language. And the last one is a development of neural network architecture for speech recognition for the automatic speech recognition models.
Рассмотрим отдельно каждый этап. Итак, создание речевого корпуса.
We'll discuss separately with all of these steps.
Значит, создание речевого корпуса. Чем больше по объему речевой корпус, создаваемый для потом уже использования обучения сети, тем точнее получается сама трансляция речи в текст.
We will discuss about the speech corpus of the Uzbek language. The creating a speech corpus is a process of reading text by groups of speakers of different ages, genders, and pronunciation based on office on the web technologies, and input text includes two topics: generally accepted books, newspapers, articles, and text documents of organization, which is a project is being executed.
Здесь представлена схема, с помощью которой значит, реализуется программа создания речевого корпуса.
Before, previously was a diagram was a development of Uzbek speech recognition system.
Значит, речевой корпус в размере несколько сот, значит, или несколько тысяч предложений, нескольких сотен тысяч слов и так далее, набирается следующим образом: либо через файл-сервер, либо через веб-сервер, либо через службу Telegram-бот. Схема представлена здесь. Слева формируется база данных, то есть сам корпус. Справа – это администратор, который, по сути, очищает поступающие речевые, значит, данные от всевозможных знаков, препинаний, всевозможных неправильно произнесенных слов. Это называется нормализация.
In the diagram shown the process of gathering of database of speech corpus. The left side is a database, and from the right side is our server. It also include the file server and web service with the administrator who will control the input of the data.
Значит, надо отметить, что правильность занесения, потому что заносится как текст, сам, который читает диктор, так и заносится аудиофайл, и соответствие текста аудиофайлу проверяется специальным оператором.
I'm going to pay for the collection of the database because using such kind of the technologies, web technologies, the administrators or personnel who will check the input data, also voice and text.
Значит, в речевом корпусе, кроме самих аудиофайлов, читаемых слов и предложений, хранятся следующие параметры: номер текстового фрагмента, номер диктора и оператора, время проверки и продолжительность.
In the speech corpus also includes speech, also the operator or personnel person or responsible person, and text, and directly the voice.
Здесь наверху представлена работа, проводимая, значит, подготовкой речевых корпусов. Внизу представлены параметры речевого корпуса, которые мы достигли.
There is shown the stage of the first is the preparation stage, and second is parameterization stages. First, the preparation or pre-processing stages consists of the inserting spaces between sentence, removal characters incomprehensible in the language, converting digital data into text, and selection of the sentence no longer than 2 or 15 words. And the second one is a speech corpus parameterization. Also consists duration around 300 hours.
Ты все цифры перевел?
Я вот рассказываю там, которые там, вот, которые...
Все цифры ты уже сказал?
Я вот начал второй параметр.
Значит, параметр речевого корпуса я хотел бы перечислить. Это значит длительность речевого корпуса 300 часов, количество дикторов, от которых брался этот речевой корпус, 882 человека, количество слов, присутствующих в речевом корпусе, 740 тысяч.
I'm going to tell about our speech corpus we create. It's a duration around 300 hours, and number of speakers 882, and the number of words around 540,000 already gathered.
Значит, поскольку проект реализуется для государственных органов, речевой корпус состоит из двух равноправных частей. Одна часть – это начитка со всевозможных широковещательных источников, книг, статей, журналов, газетных публикаций. Вторая часть формируется из тех документов, тех государственных органов, ради которых мы делаем, то есть из их постановлений, из законов, из всевозможных директивных решений, а также протоколов их совещаний.
This project dedicated to the government, especially justice, so that this project has a two-part. First part for speech corpus gathered from open access libraries, open access books, open access web contents. And the second part from spatial part, which is given from the government. It's some kind of decrees and some kind of rules, something like that.
Перейдем к третьему этапу. Значит, после речевого корпуса рассмотрим последовательность алгоритмов выделения информативных признаков в соответствии с той таблицей, которую я показал в самом начале.
We will talk about the last part is the directly processing of the speech signals.
Так, итак, последовательность алгоритмов представлена на, значит, слайде. Речевой сигнал.
In this slide is
Так,
shown the
естественно, речевой сигнал аудио переводится, естественно, в цифровую форму. и делается на первом этапе его предварительная обработка. То есть это оцифровка, входит сюда, фильтрация с фильтром конечной импульсной характеристики, и также задача спектрального анализа преобразования Фурье.
In this presentation are shown the algorithms for speech extraction or extraction for informative features of the speech. They are pre-processing. It means the filtering, segmentation, and window or Hamming. And second is spectral analysis. It means the fast Fourier transform and other transforms. Second is mel frequency capture
Это я еще не
coefficients.
дошел. Следующее, фильтрация с помощью алгоритма, значит, Mel Frequency Capsule Coefficients, это МФК, потом идет алгоритм DST, это Discrete Cosinus Transform, и идет процедура логарифмирования, и в конце получается МФК спектрограмма.
Okay. Last stage is getting Mel frequency capture coefficients and the discrete cosinus transform. And after discrete cosinus transform, we got a logarithmization. And after that, we got a capture coefficients features.
В результате получается спектрограмма, по сути, для каждого текущего фрейма речевого сигнала. Фрейм, значит, аудиосигнал с микрофона после цифрового представления в цифровом виде разбивается на сегменты, так, по 25 миллисекунд.
In the result, we got a capture coefficients of each frame. You know, the frame is the division of the speech signal into some short parts for getting the feature.
Над каждым из этих фреймов проводятся вот и указанные здесь процедуры, это уже следующее, и мы получаем в результате кэпстральные коэффициенты, кэпстер.
For each frames, we got we do these stages, processing stages, and got the capture coefficients.
Все, дальше пошли. Четвертый этап. Архитектура для получения акустической модели речевого сигнала.
Second stage is the architecture for the acoustic model of a speech signal.
Здесь представлена, значит, глубокая нейронная сеть, где на входе то, что мы говорили, кэпстер в виде спектрограммы, и дальше идет уже ее обработка. На первом этапе, здесь написано все, да, на первом этапе, значит, получается использование сверточной и рекуррентной нейронной сетей и реализуется алгоритм глубокого обучения. Это CNN и BLSTM.
First stage is a deep neural network. It's also which is consists from two-dimensional convolution neural network and recurrent neural networks.
Значит, на первом этапе с помощью двух первых этапов, значит, CNN и BLSTM получается карта признаков и в виде свернутой или компактно представленной спектрограммы, из которой выделены информативные признаки.
For the first stage, we got informative features after doing the from spectrograms the convolution neural networks.
Следующие два блока посвящены тому, что формируется, значит, матрица вероятностей букв и слов, и в конце получается текст букв, отдельных букв узбекского алфавита.
Last two stages is getting the features for the each Uzbek words, and in the last we will get the all our words separately, our Uzbek words.
Это общая схема, использованной нами глубокой нейронной сети.
It's general scheme or stages of which we used it during our speech processing system.
Теперь посмотрим, как с помощью этой схемы создается акустическая модель сигнала.
Now we are going to talk about using with this scheme how we create the acoustic model of the speech signal.
Акустическая модель – это функция, принимающая на вход небольшой участок акустического сигнала, кадр или фрейм, и выдающая распределение вероятностей различных фонем, то есть букв, на этом кадре. Следующий.
The acoustic model.
Нет, следующий. Ага, все.
The acoustic model, it means that doing some pre-processing system and going doing some processing algorithms and getting some parameters or features.
Итак, рассмотрим по ступеням. Мел-спектрограмма речевого корпуса пропускается через сверточную двухкаскадную нейронную сеть CNN, то есть сверточную сеть, на выходе которой формируется карта признаков, то есть признаков фонем, признаков тех информационных частей спектрограммы, которые для нас представляют наибольший интерес. Это максимальный информационный фрагмент.
And first stage is Mel spectrogram speech signals or speech words. After doing two-dimensional and convolution neural network, in output we got the feature card, which is after doing the processes around 40 features we will get after doing this process.
Карта признаков поступает на вход рекуррентной сети BLSTM, так, во входном слое которой непрерывное изображение карты признаков преобразуется в последовательность дискретных значений.
After that, the feature card goes to as an input of the recurrent neural network BLSTM.
Для формирования на выходах BLSTM на каждом шаге вероятностных значений векторов использована полносвязанная нейронная сеть Хопфилда с 29 выходами. Это 29 букв узбекского алфавита.
In the output of the BLSTM, we will get the neural network of Hoffield with 29 29 features. It means that 29 the Uzbek words.
Для каждого фрейма уточняется вероятностные возможности весовых значений букв алфавита, в результате чего создается матрица вероятностей. Матрица вероятностей, связывающая поступающий вектор, значит, фрагмента аудиосигнала и соответствие его букве узбекского алфавита.
In the output, we will get the frame of each words, which has some kind of connection with Uzbek words for doing some prediction.
Значит, поскольку в одном фрейме может содержаться несколько вероятностных букв, значит, программа STS удаляет лишние буквы, оставляет по одной. Таким образом формируется транскрипт из 29 узбекских букв.
In each frame, they may consist of several characters of Uzbek words. With a program of STS, which was created by our lab, and it removed some characters, and after that we will collect the full characters of the word.
Затем эту процедуру выполняет STS, Connection Temporal Classification.
And after that, this function will do with the function of connection temporal.
Вот это то, что я рассказывал, это делается в процессе машинного обучения.
All of this process are include our machine learning system, which is created by our lab.
Приложение паста, паста, приложение B2. Pasta приложение B2. Mayli. Eng pastida oxirida. Заключениdan keyin birinchi tablitsa, вот. Да, shumi? Yo'q. Birinchi. Birinchimi? Вот. Значит, здесь в таблице даны параметры сети при создании акустической модели для 2D convolution, для рекуррентной сети, полносвязной сети FS, так, полносвязной и слой транскрипции STS-loss функции, а также даны параметры обучения, длина шага и размер батча.
In this table are shown the input parameters for the acoustic signal processing. For the input is a two-dimensional convolution part, where which is the consists filters and function ReLU. It means and next one is also is for each part we did a recurrent and BLSTM neural networks with layers of 520.
Так, создание языковой модели. В процессе обучения, кроме акустической модели, значит, компьютер обучается языковой модели. Почему? Потому что есть распознавание отдельных слов, а есть распознавание целого предложения. Поэтому отдельные слова делаются в процессе обучения, значит, акустической модели, а уже само предложение формируется в результате обучения языковой модели. Мы рассмотрим теперь языковую модель.
There is a language model because we have in processing or also in speech processing we have two type of processing. First is processing limited some words, only words, and also we may recognize the full sentence. Here is shown the stages of the recognition, the whole sentence or continuous speech.
В данном варианте реализации использовано 350 тысяч предложений узбекской речи.
In this during the development of this process are used 350,000 Uzbek words.
Для реализации языковой модели было использовано так называемые n-граммные модели. N-граммные модели применяются в системах, значит, перевода, машинного перевода, так, и в реализации n-граммных моделей также участвуют рекуррентные нейронные сети на базе рекуррентных нейронных сетей.
For the doing language model, we used n-gram models, which is used also in recurrent neural networks. It's a part of machine learning.
Представлена схема, последовательная схема, значит, состоящая из алгоритмов one-not vector, с помощью которого определяется битовая последовательность слов в соответствии с алфавитом.
In this diagram is shown the stages of creating as a language model. First is one hot vector. After this one, we will get the feature as a bits.
Алгоритм embedding осуществляет поиск словарей из 100 тысяч слов.
The algorithm is embedding for the searching the directly words in our database. It's around 100,000 words.
Сеть LSTM сохраняет вероятность последовательности слов, а для формирования на выходах LSTM и EFS вероятных значений используется слой нормализации softmax.
The LSM consists of the feature of these words. For the output is next is stages FC and softmax. It will be the input, the feature.
Здесь представлена таблица, где даны параметры тех нейросетевой архитектуры, с помощью которых создавалась, значит, языковая модель. Это входной слой, embedding слой, рекуррентный слой, полносвязный слой и параметры обучения, длина шага обучения и batch size.
In this diagram shown the input parameters for these stages. It consists embedding layer, recurrent neural network layer, and are the parameters for the machine learning.
Значит, получилось так, что мы сделали два шага обучения. Значит, обучили глубокую нейронную сеть, обучили понимать слова, находить слова из аудиофайла. И второе, находить последовательность слов в предложении того же аудиофайла. Теперь перейдем к модулю, который работает уже, когда диктор, пользователь, начинает говорить.
We did two types of learning. It's first, it's for learning exact words, and after that, the learning for the sentence, and the last one is a part of where the speech signals with can be recognized by our the system.
Итак, модуль автоматического распознавания речи. Значит, после реализации алгоритмов машинного обучения и выработки акустической модели на выходе глубокой нейронной сети формируется транскрипт речевого корпуса.
Model automatic speech recognition. After doing some processes in output, we will get the features for the directly recognition.
В результате создания языковой модели получается выражение для последовательности слов на основе большого тренировочного корпуса узбекского языка.
For the language model, we will get the sequence of the sentence, which is may use it for the processing the sentence.
Получается, что при автоматическом распознавании мы используем как акустическую модель обучения, так и лингвистическую информацию.
From this, I may say that for the speech processing Uzbek signal, we can use two kinds of acoustic model processing and linguistic processing part.
Итак, автоматический режим распознавания речи, то есть тогда, когда пользователь уже начинает использовать ее в своей работе, значит, используется предварительная обработка, опять же, когда он говорит, уже идет оцифровка, фильтрация, сегментация, общие процедуры спектрального анализа, выделение информативных признаков, автоматическое распознавание с использованием акустической языковой модели и формирование выходного текста. То есть, получается, в основном этапы, которые были пройдены при разработке акустической языковой модели.
In acoustic model processing, we use pre-processing first of all. It means filtering, doing some kind of windows or Hamming windows, and getting some features like a capstar coefficients, and it will be used as a
Использование акустической языковой модели.
Yes, using the acoustic language model,
и формирование выходного текста.
and after that we will get the output text. As in input is the speech, in output is the text.
Итак, представлена схема, полная архитектура и основные компоненты предлагаемой в проекте многослойной нейронной сети.
In this diagram, I shown the architecture of the processing based on the multi-layered neural networks.
Значит, на первом этапе спектрограмма с помощью сверточной сети и создается карта признаков. То, что мы говорили в процессе обучения акустической модели.
In the first stage, we will get the spectrogram as a feature card for the neural network.
Сеть LSTM и сеть FS в результате подготовки языковой модели формируют матрицу вероятности.
Using the net of LSTM and FC, we will get the table or feature map.
Задачей декодирования STS-декодера является
The aim of the or purpose of the DST decoder is
использование результатов работы акустической модели и языковой модели для создания выходного текста.
It uses for the import data from the acoustic model parameters.
И при этом используются результаты обучения как акустической, так и языковой модели.
And after that, we will learn also results acoustic model, also is language models together.
В декодировании очень много используется комбинаторных алгоритмов, следовательно, реализуется огромное число переборов при поиске слов, подходящих для данной концепции, значит, самого языковой модели, и требуется внедрение эффективных эвристических методов для практического решения задачи.
Using decoders, we may do some search processes, because, for example, from the data which consists around more than 1,100 data, we have to find the exact word for the recognition.
Теперь я хотел бы рассмотреть вот здесь внизу. Хотел бы рассмотреть оценку качества распознавания.
Now, I want to talk about the results which we got for estimating our results.
Итак, оценка вычислялась по двум критериям. Word error rate для ошибочных слов при каком-то текстовом проверке. И по критерию character error rate это ошибки всевозможных знаковых пропусков. Получилось по VER у нас 16,2%, по CER у нас 5,4%.
Estimation did with a 2-point or with a 2 formula. It's where it means word error rate, and second is a character error rate. Word error rate 16.2% was, CER was 5.4%.
Это надо понимать так, чтобы цифры вас не смущали. Если перевести в понятную для вас позицию, это примерно 90% правильного, значит, с точки зрения слов, и еще более точно с точки зрения неправильных символов.
It means that it's if we convert it into the accuracy, it's around 90% accuracy of the words, and the character error rate is a 5.4%. It's higher than 90% accuracy.
Так, следующий давай. Синтез. Значит, я здесь рассказал вам об анализе распознавания человеческой речи. Теперь мы перейдем ко второй половине, значит, проекта, который называется синтез. То есть технология, текст речи.
Before we talk about analyze or processing of the Uzbek signals, now I'm going to talk the second part of our project is a synthesis of Uzbek signals.
Значит, особенности работы с синтезом речи заключаются в том, что требования к синтезу речи — узнаваемость, естественность, выразительность и правильность расстановки пауз.
The aim of the synthesizing or of the speech signals is consist of the
Узнаваемость, естественность,
is naturality or recognizability
выразительность
and presentability
и паузы, правильной расстановки,
and
и ударение.
pronunciation should be given the right form.
Основная задача заключалась в том, чтобы, когда идет синтез речи, чтобы он не говорил как робот, чтобы он говорил нормальным человеческим языком.
The synthesis system should be the natural language, not like as a robot or the words synthesized by the robots.
Значит, здесь представлена общая схема внизу, к сожалению. Я не знаю, видно вам или нет.
There is shown the general diagram of the speech synthesis system,
Где реализуется в процессе синтеза речи, реализуется анализ текста, то есть входным является текст, выходным является естественная человеческая речь. Идет, значит, алгоритмы анализа текста, лингвистического анализа и генерации самой речи.
Speech synthesis system consists the several parts. First is a text as an input. And last stage is the analyze of this text, and second is a linguistic analyze, and third is a generation of the speech, and in output we will get the synthesized speech signal.
Теперь я хотел вам представить существующую классификацию систем синтеза речи. Значит, те, которые широко применяются, в том числе у нас были уже защиты диссертации, где использовались эти подходы. Это параметрический синтез, конкатенативный синтез, статистико-параметрический синтез и гибридный синтез.
Now I'm going to talk about classification of the synthesis of the speech, which is globally uses or used in many systems, or they are first is a parametric synthesis, second is a concatenative synthesis, third is a static parametric or feature synthesis, last one is a hybrid synthesis.
Кратко перечислю их особенности. Параметрический синтез – это на первых этапах разработки систем синтеза речи использовались, когда формируются отдельные параметры, формат речи, подбираются слова, через опыт пользователей подбираются всевозможные параметры их, и при анализе текста они генерируются.
Parametric synthesis, it means that during acoustic processing, they will generate the speech, and for each text, we will connect this text.
Конкатенативный синтез – это более широко применяемый, когда заранее записываются, значит, слова и их фрагменты, слоги слов отдельно, большой речевой корпус набирается, затем они маркируются и сегментаются в единицы, и в процессе того, как человек вводит текст, набираются подходящие единицы для формирования фонограммы.
Concatenative synthesis, it means that also is widely used the method. First of all, we prepare the audio with a huge of the speech, with the tokens, with the symbols, and the second is labeling and segmentation part, and the last one is the preparing the words for exact text.
Надо сказать, что такой вид синтеза требует очень большой базы, причем от базы сильно зависит качество. И тем не менее, системы, работающие на методе конкатенативного синтеза, ну, речь произносят как робот.
Using this method, we need some spaces is for the big data for the collecting the words, and after doing these methods, especially it's not near the natural language synthesis words. It cannot be as a natural language.
Следующие статистики открою. Значит, в статистико-параметрическом синтезе для последовательности слов, хранения этих слов и так далее, при реализации текст, анализ текста, генерация признаков и генерация формы волны используются марковские цепи.
For the statistic parametristic or statistic feature synthesis, it uses for the generating the speech signals Markov chains or Markov models.
И, наконец, используемый нами гибридный синтез речи, схема его представлена на плакате.
Here in this diagram is shown is a hybrid synthesis model, which is developed our lab, or we are using in our project. Is shown in this diagram.
Гибридный синтез речи делает более глубокую проработку речевого корпуса, разбитие его на отдельные фрагменты, делает предобработку этих фрагментов, то есть формирование фонемных слов и предложений. Затем акустическая модель формирует из нее мел-спектрограммы, о которых мы уже говорили, и затем уже вокодер генерирует, так сказать, естественную человеческую речь.
Hybrid synthesis model consists from the it's based on the deep neural networks also, and in acoustic models we may do some pre-processing and for the getting tokens and the words of the acoustic model, we will get frequency capture coefficients. It comes to input as a neuron vocoder.
Значит, кратко, предварительная обработка, первый этап, это обычная предварительная обработка, когда текст преобразуется в лингвистические характеристики в виде вектора, вводимого в акустическую модель.
As a first pre-processing part in the phonemes, also the input parts becomes as a linguistic parameters or linguistic vectors.
Акустическая модель представляется для преобразования предварительно обработанного текста в мел-спектрограмму.
In an acoustic model, this input data becomes as a mel frequency captures.
Акустическая модель, при разработке акустической модели использовался пакет Токатрон 2.
In an acoustic model, we are using some libraries or software packets.
Теперь при формировании речевого корпуса, так, это очень сложная большая задача, поэтому существуют готовые с открытым кодом речевые корпуса разных языков. Я могу перечислить вот Libre Speech на 1000 часов, Vox Cable на 60 гигабайт, Spoker Wikipedia, Corpora и так далее. В России это RusSpeech, речевой корпус, разработанный для русскоговорящих пользователей.
Now I'm going to talk about the preparation of the speech dataset speech corpus. It's a very big part of speech processing. Also, I'm going to talk about. We already have too many already prepared speech corpus, especially in Russia, in other language, especially for the English language. There has already huge data.
Теперь я хотел бы рассказать про эксперименты и результаты проведенных нами исследований в области синтеза.
Now I'm going to talk about the results which are taken during our research.
Значит, общий объем речевого корпуса узбекского языка составил 25 часов 40 минут.
During the experiment, the whole volume of Uzbek speech corpus was
25 часов 40 минут.
25 hours, 40 minutes.
Генерация осуществляется в два этапа. Первый этап – переход с текстовой формы в mail-спектрограмму. Второй этап – переход с mail-спектрограммы в аудиофайл.
Generation starts developed in two parts. First is from acoustic model to from the text to acoustic model, and second one is from acoustic model to.
Здесь представлена схема подготовки речевого корпуса. Должен сказать, что подготовка речевого корпуса очень скрупулезный процесс очистки его. Почему? Потому что диктор, говорящий на узбекском языке, он должен говорить равномерно, четко, произнося каждую фразу, каждое слово. От этого зависит качество уже генерации самой.
In this diagram, I'm going to pay attention the process of filtering or preparing the words, because right pronunciation also may give some results during getting accuracy, because the failed words it becomes getting the low accuracy.
Здесь на схеме представлена обработка идет как аудиосигнала, так и текста. То есть того текста, который читает диктор, и того аудиосигнала, который фактически он произносит. Оба равноправно обрабатываются.
Processing part consists of two parts. First is the processing of the signal, and second is processing of the text. They will do these words, process. You have to do in a concurrent time.
Текст, предобработка – это очистка от неправильно произнесенных, неправильно записанных символов, неправильно записанных слов. Нормализация текста – это исключение слов иностранного произношения и также исключение неправильно произнесенных слов самим диктором. Дальше сегментация текста предложения, то есть отделяются предложения длиной 2-5 слов.
The text processing part consists pre-processing. It means doing some processing algorithms with the text for the preparation. Second is a normalization of the text. Also is there is we know the too many types of the text will be in our data, and the third one is a segmentation of our text for the processing.
Аудиосигнал тоже проходит предобработку, так же, как мы раньше рассматривали. То есть предобработка идет очищение, разбитие на сегмент, удаление зон молчания, вырезание неправильно произнесенных слов. И таким образом мы имеем обработанные предложения в текстовом виде и обработанные речевые фрагменты.
The audio processing part is also consists in the pre-processing of the signals, and also is segmentation, and extracting the pause and silence part of the speech signals. And after that, we will get two types of features. First is the text, and second is audio features.
Дальше идет синхронизация этих двух половинок. Создается транскрипция текста и транскрипция аудиофайла. Таким образом, речевой корпус оказывается сформирован.
After that, we will do synchronization of these text and audio signals. And after that, we'll do the transcription, text and audio files for the generating of our speech corpus.
В данном случае мы использовали пакеты Тракатрон и параллель WiFGAN, в состав которых входят глубокие нейронные сети.
For the preparing our speech corpus, we use the two types of the libraries. It means Tracatron and parallel wavegun.
Вот эту часть работы, синтез, мы уже сдали государственным органам, провели тестирование, проверку. Сейчас она находится на эксплуатации. В случае нахождения каких-то, может быть, ошибок или нечетностей, значит, мы исправляем. Эта часть работы уже сделана и сдана.
This part of the project already is finished, and we give to the government. They are testing now. If some mistakes or some mistakes occurs, they will tell us. We will change. And now already is finished this part.
Что касается первой части, анализа или распознавания речи, в принципе, мы основные разработки сделали. В настоящее время идет добор речевого корпуса. Значит, пока у нас еще немножко, примерно не хватает 150 тысяч, поэтому после доработки, я думаю, в конце года мы уже будем предъявлять на экспертизу, на эксперимент, на экспертизу своему заказчику передавать первую часть, которая называется анализ узбекской речи.
About first part of our project is analyze or recognition the Uzbek signals. We did all research, and we have algorithms, which is the results of algorithms show that we are in the right way, and also is a good results. In that part, we are now still gathering our speech data corpus. We need also around 150 hours.
И в заключение я привел, давай следующий. В заключение я привел стандартные средства, которые использовались, во-первых, для систем speech-to-text, раз, и стандартные средства для систем text-to-speech.
In a conclusion, I may say that there are, you may see the two types of the already existing the technologies for the speech to text and also text to speech.
Right. Thank you very much. Спасибо за
Thank
внимание.
you for your attention. If any questions, we are ready to answer.
Там подними немножко. Там есть email. Если у кого какие-то вопросы или интерес к данной проблеме, пожалуйста, обращайтесь. Я готов.
There is my email. If you have any questions or some discussions, don't hesitate. Please write me to this email. I'm ready to cooperation and answer your question.
Все.
Thank you very much.
Sir, may I ask one question?
Okay, you may ask.
Yeah, what is the environment you have recorded audio, your speech data? That is one.
For the collecting speech corpus, you mean?
What is the environment, and means what are the tools and what conditions you have used a test data and trained data. Another question is, what is the language perplexity of your data set?
Okay, first question was what environment we are using for collecting data, right? Okay.
Because you have used a noisy environment or normal environment or pure the recording mode kind of thing, any of these things.
Существует международный ресурс речевых элементов. Я уже сказал, что там есть английские, всякие, и в том числе русская речь. Мы использовали оттуда только небольшую часть, несколько десятков, сотен, значит, предложений и слов, часов. Почему? Потому что, я уже сказал, у нас состоит из двух частей. Есть общая часть речевого корпуса, которая берется из широковещательных, часть, которая предназначена специально для той организации, для которой мы делаем. Поэтому много оттуда мы не взяли. Взяли всего 100 часов примерно, 90-100 часов взяли.
For gathering, we use it also during the collection of our data. In some parts, we also used some open access libraries. And after that, in some parts, we create or developed our application. And also we use the open access data around 100 Uzbek speech corpus, and last other part we are creating by ourselves.
Так, еще вопрос?
Is it all clear?
Yeah. So if it is your data, what is the performance of the system, sir? Sorry, this is last question. For your collected data, what is the performance?
Performance, you mean that it's this project, we did this project for our government. This project consists two parts. It's first is the synthesis of Uzbek language. It's a text to speech, and second one is analyzed part. It means the recognition of Uzbek speech. It means that speech to text part for justice.
Okay, thank you, sir. I got it.
Thank you very much. If you have any questions here, you may write directly to the professor for the new collaboration, and for if you have a much, also any questions, don't hesitate.
Пожалуйста. Это не дискриминация. Дело в том, что с точки зрения аккуратности чтения женский голос лучше. Но другое дело, что, как говорят узбеки, нам нужны были кандидатуры из разных областей Узбекистана. Чем больше мы охватываем хорезмскую, ферганскую диаспору, сурхандаринскую, самаркандскую, ташкентскую, тем богаче речевой корпус. Почему? Мы же делаем диктора независимый. Значит, любой гражданин Узбекистана имеет право обратиться, в смысле, пользоваться этим. И если мы не учтем это, как говорят узбеки, произношение из этих областей, то, конечно, неточность будет появляться неточность. Но мужиков достать из областей оказалось легче, чем женщин.
The question was during the collecting of data, why you use 6,500 men and 35% is women. It was some kind of joke question. Why are discriminating? The answer was it's not discrimination, because women can clearly record the words. Also, during research, we see the woman's words is clear, and also we have several dialects. For example, Harizm and the Surkhandara region dialects, they has totally different. So that in this opinion, we got more men data for our speech corpus.
Так, еще, пожалуйста. Трудности. Сейчас я скажу. Здесь мы опустили эту часть, мы не стали ее рассматривать, морфологический анализ, потому что это была подготовительная работа. Но я вам скажу, что такая работа проводилась, Мы разговаривали с узбекскими филологами, специалистами по филологии, и они выделили для нас особенности узбекского языка, который отличается от английского, от корейского. Наличие у нас в узбекском языке некоторых букв, которые там отсутствуют из звуков, таких как «к», таких как «г», да, и несколько таких звуков. Естественно, что мы должны были это учесть. Мы это учли, и, посоветовавшись с ними, при формировании речевого корпуса мы увеличили количество слов, содержащих такие буквы и такие выражения. Поэтому эта работа проводилась, просто здесь она не изложена. Мы здесь изложили уже основные результаты.
Here is also in this part we already did research. Here we show as the pre-processing. It includes all this morphological analysis also. We have in our characters, we have different pronunciation characters, for example, something like that, which is also has no even in English or in Russia or also in Korean language. We with our other colleagues from language university already discussed, and for gathering our corpus, we already have before learning these kind of words with this kind of tokens.
Например, от русского языка отличается тем, что в русском языке есть ударение, в узбекском языке ударения нет. Значит, получается, при извлечении данных из спектрограммы мы должны были это учитывать. Это раз. Во-вторых, в отличие, скажем, от южноазиатских, скажем, китайского, корейского, у них больше гласных, у нас больше согласных в речи. Это, конечно, учитывается.
Also in Russia, during pronunciation, you have to pay attention. Even one word may two different opinions. So that, but in our language, we have not that kind of attentions. So that we discussed with our colleagues and did huge the works in this direction.
И я хотел бы еще к вашему вопросу добавить, что до сих пор не существует, вот только создается модель узбекского языка. И нам пришлось приводить очень много экспериментов с помощью нейронных сетей для того, чтобы создать акустическую модель. Мы ее создали, вот, но она продолжает совершенствоваться с помощью вот взаимодействия с филологами.
I want to add that we did a huge work, research work in this area, but it means that it's not finished. Now we are working together. We are improving even our system, so it's not finished yet.
Есть еще вопрос? У кого вопрос? Спроси, у кого? Есть вопрос?
If you have any question,
Thank
thank you very much.
All right. So thank you very much, Professor Musaev, for a great speech. And I can see that lots of professors and researchers are taking interest in your research field, and hope they will like to collaborate with your research work. And thank you very much for your speech. Thank you, Professor.
Katta rahmat sizning nutqingiz uchun. Ko'rinib turibdiki, sizning o'sha ilmiy ishingizda bir nechta juda ko'p ilmiy o'sha insonlar qatnashgan va juda ham katta ishlar olib borilgan. Katta rahmat nutqingiz uchun.
All right. Thank you. All right. So our next keynote speaker is Professor Venkat. He's already here online, I can see. So Professor Venkat, for about Professor Venkat, Dr. Negora is going to introduce. Please come here. And please allow to see everything.
Thank you, Dr. Dhananjay. Now, it is my privilege to invite Professor Venkata Subramanian Ganesan on stage, like online, to deliver his presentation on the topic of Bayesian brain and schizophrenia. He is a psychiatrist and clinician scientist who works as a professor of psychiatry at the National Institute of Mental Health and Neurosciences in Bangalore, India. Professor is known for his studies in the field of schizophrenia, transcranial direct current stimulation, brain imaging, neuroimmunology, neurometabolism, and several other areas of biological psychiatry. The Council of Scientific and Industrial Research, the apex agency of the Government of India for Scientific Research, awarded him the Shanti Swarap Bhatnagar Prize for Science and Technology, one of the highest Indian science awards, for his contributions to medical science in 2018. Professor, you can start. Thank you.
So good afternoon.
We can hear you, Professor. Please go ahead.
Yes. Thank you. At the outset, I wish to thank the organizers for this opportunity, Professor Dhananjay Singh and his colleagues. And it is nice to interact with a galaxy of light and eminent scientists through this platform. And thanks a lot for the generous introduction. The title of my presentation would be Bayesian Brain and Schizophrenia. So schizophrenia is a psychiatric disorder, and which has a prevalence of 1% in the general population. As we could see in this slide, this is a disorder where the brain development of the individual, even at the time of pregnancy, that is at the fetal stage, is affected. And what happens as the brain develops in people that carry the risk for this disorder is there are a lot of abnormalities that unfold during the adolescent brain development, and usually in the second to third decade of life, the symptoms of schizophrenia starts manifesting. Some of the specific symptoms of schizophrenia that I would like to highlight are hallucinations and delusions. Hallucinations are experiences that will happen in the absence of any stimulus. For instance, if I have to have hallucinations in auditory modality, that is hearing some kind of noises or voices, we'll call it as auditory hallucination. And I can hear people talking to me or multiple people talking to each other without anybody actually being around. So this is the auditory hallucination profile, whereas delusions are essentially false beliefs without any basis. That is, I may believe without any evidence that people are trying to harm me. So these are some specific symptoms of schizophrenia, that is hallucinations and delusion. There are also other types of symptoms that happen in this disorder, which is speech-related problem, where the speech is not very well organized. The previous scientist presented very interesting literature and research on the language and the thought-related expression, that is speech analysis. So perhaps there is a lot of potential application of such research techniques in understanding the speech disorganization in schizophrenia. The speech disorganization will also be associated with behavioral disorganization, and also there are certain symptoms which are called as negative symptoms in schizophrenia, which essentially describe the state where a person is not so much motivated in doing things, in talking, in participating in various activities. In this particular presentation, I'll be specifically focusing on hallucinations, which can be simplified or summarized as imaginary voices, and delusions, which can be surmised as false beliefs. Now, if we look at the brain abnormalities in people with schizophrenia that is believed to underlie the genesis of these clinical symptoms, research suggests there could be abnormalities that involve GABAergic interneuron, that is gamma aminobutyric acid, which is an inhibitory neurotransmitter, as well as glutamatergic abnormalities in the brain, which especially involves the pyramidal cell. Because of this GABA abnormalities, the brain rhythm, especially in the gamma frequency, gets affected, and that is believed to underlie the genesis of some of the symptoms of schizophrenia. This is from the perspectives of a brain rhythms basis. On the other hand, there is also research that suggests certain neurochemical abnormalities involving dopamine could underlie the genesis of these symptoms. So there are multiple levels of abnormalities in the brain that have been documented. A set of abnormalities that involve brain rhythm disturbances, a set of abnormalities that involve neurochemical disturbances, which essentially is found to underlie the manifestations of symptoms like hallucinations and delusions. If we have to look at hallucinations and delusions from neuroscientific perspective, they link with how we perceive and how we believe in what we perceive and what we believe. So this is the context in which I will link schizophrenia with Bayesian brain in the coming slides. Now, if you want to understand schizophrenia, the significance of perception is paramount. If I have to put it in a very profound statement published by eminent authors and scientists, I may want to say, if we want to understand the hallucinations, which are false perceptions, and delusions, which are false beliefs, we need to explore the interaction between the physical and the mental. To explain how a mental phenomena emerges from a physical interaction, perhaps is a key challenge that faces the 21st century science. Here, the science of perception offers a unique opportunity to understand this interaction, that is the physical versus mental interaction, and its relevance for schizophrenia. So if you want to look at the theoretical perspectives of perception, there are two major theories. One is a passive perception, another one is an active perception. In passive perception, the postulate is organ which just receives the external stimulus, it does some processing and gives motor and autonomic responses. Whereas in the theory of active perception, there is a proactive involvement of the brain is postulated. That is, the brain samples the environment for predicted stimulus. At the same time, it also predicts what are the likely external stimuli. So these two processes go hand in hand, and the brain compares and also contrasts it with the intention with which it predicts the likely external stimulus. And this kind of active process results in a percept, or results in a stimulus getting perceived by the brain. So this kind of active perception can also be called as constructivist perception, where the perception involved in based on association of ideas and previous experiences. So what we see here in this slide is a German polymath, Worm Helmholtz, who has kind of emphasized this postulate of active perception. And there is interesting recent developments that are coming as an offshoot of some of the theoretical postulates emphasized by this scientist. Now, if we look at constructivist or perceptive brain, it can be called as a fantastic organ. The word fantastic organ originates from the Greek word fantastikos, which means the ability to create mental images. I'll give an example to illustrate this. In this slide, on the left-hand side, we see an image, which is the painting by Arcimboldo. This is a very famous painting, which is called as the vegetable in a bowl at one level. So what we see here is a vegetable bowel, the black colored container here, and there are a few vegetables that we see. Now, without making any changes in the content of the image, if the image is inverted, now we will be able to see the bowel as a cap and some of this vegetable getting to form a probable face. This could be seen as the nose, and this could be the cheek and the lips. Now, the same image which was perceived as vegetables in a bowel could be seen as a face. So this is called as the vegetable gardener's face. So this is a famous painting which has attracted a lot of neuroscientific interest. So here, this particular instance is an illustration that the brain has the ability to create mental images, even though the stimulus that comes from the outside remains the same. The way in which the brain sees could help it to create certain mental images and infer from them. So this is immediately relevant for the concept of Bayesian brain, because constructivist approach suggests that perception is a process of probabilistic inference, and this inference is generated by applying a probabilistic model that can generate predictions against which sensory samples are tested to update beliefs about their causes. So in essence, the brain uses a Bayesian probabilistic model. And to refresh about the Bayesian theorem, we know that Bayesian theorem permits us to compute an updated probability of something is true based on the old probability, and some new information is added. So the brain in this context can be conceptualized as a Bayesian probability machine that constantly makes prediction about the world and then updates these predictions based on what it senses. So how does the brain in Bayesian perspective implement these kinds of mental image creation? So this is where there are several scientists that have proposed the concept of predictive coding. One of the prominent contemporary scientists that work in this area is Carl Friston. And this postulate of predictive coding can be summarized as: we see what we expect and we expect what we see. I'll give another example to illustrate this. If you see in this slide, on the left-hand side, there is an image. If I am asked, what do I see? I may think that perhaps this image could be formed by a dog, a canine. So here, the Bayesian brain processes the incoming information, that is the shadow. And if I am asked to predict, and I will predict based on my prior expectation that this image could have been caused by a dog. So this kind of processing involves predictive coding. Now, if I am given some more information, like what we see here in this slide on the right-hand side, it's a bit unusual situation where it appears a cat has resulted in making an image that resembles that of what would have been caused by a dog. So here, I'm now getting a new sensory information, and this sensory information of cat being the possible source of origin of this shadow is not matching with what I expected. That is, this particular sensory information does not match with my expected model or prior, and this mismatch will result in a prediction error. Now, my brain will update or retain the model depending upon whether the incoming sensory data is of high quality or high precision or low precision. So if this kind of prediction system is imbalanced, I may derive some faulty inferences leading to false beliefs and false perception. For instance, if I have to have schizophrenia symptoms, initially I believe that this image is caused by a dog, and then I am getting to see possibly it is a cat which might have caused the image or the shadow. But I will still believe in what I was expecting earlier. I would say that maybe there is a dog which is disguised as a cat. Maybe something a conspiracy is going on, and that is why even though the cat is there, the image looks like that of a dog. So I may derive several such faulty inferences which can be clinically inferred as delusions. So in essence, the postulate of a Bayesian brain proposes brain as a hierarchical prediction machine. And in this predictive processing framework, brain is cast as a hierarchical prediction machine that uses belief updating schemes to approximate Bayesian inference by utilizing priors. Priors are nothing but the probability distribution about the hidden states of the world and incoming sensory data. That is, if there are some prediction errors which doesn't match with the expectations, then there is a posterior estimate based on the Bayesian model, which is the best guess of the hidden cause of the sensory signal. So this is, in essence, the postulate of Bayesian brain. Now, with respect to schizophrenia, I was talking about the delusions and hallucination. Here, there could be some problems and some kind of abnormalities that happen in the way in which brain the causes of the sensory information, and the theories as well as some of the emerging evidence suggests that when the incoming sensory data violate the prediction error signal which is sent to update the predictive model. But what happens in schizophrenia? I have used the term psychosis here. Psychosis is a relatively generic term which refers to some of the psychosis symptoms like hallucinations and delusion. So in psychosis, which is a part of the schizophrenia disease, the balance between the predictions and the sensory data is proposed to be disrupted. And this disruption could be because of some of the initial abnormalities I mentioned, that is the dopamine related abnormalities or the glutamate acts through the NMDA receptor. So these receptor based abnormalities could be the reason for some of these clinical manifestations. Now, let me try and link the Bayesian brain to some of the clinical experiences that we find in schizophrenia patients. Now, if I have to have schizophrenia experiences, there is one striking symptom that is called as delusion of alien control, where the patients fail to recognize self-generated movements. And these movements are recognized rather as externally generated. For instance, if I have to have this kind of alien delusion experiences, I may say, as I am speaking, I may say that it is not me who's speaking. There is a force that is moving my lips, and I began to speak, and the words were made for me. In Bayesian terms, the brain fails to predict and differentially infer self versus non-self. So now, what is the fundamental neuroscientific mechanism that helps us to distinguish self versus non-self? There is a postulate called corollary discharge. This is a mechanism, or this is a paradigm in which the brain's ability to distinguish self versus non-self is recognized. Corollary discharge mechanism refers to the suppression of sensory consequences of self-generated action. Now, as I keep talking, I am also moving the slides. I am pressing the computer mouse, due to which the slides move. Now, if we want to look at the neuroscientific occurrences in terms of the brain changes that happen as I perform all these actions, now, if I have to press the computer mouse, there is a motor instruction which is generated by my brain, which results in the motor act. As I perform the motor act, there is a feedback which goes from the periphery to the brain, which is called as the proprioceptive input. which goes through the nerves and reaches the brain. And this kind of feedback is called as the reafference copy. Now, as my brain makes this motor instruction, there is also another neural signal, which is called as the efference copy, which is also generated. Within the brain, in the paradigm of corollary discharge, the postulate is there is a comparator or a self-monitoring system within the brain, which tries to match the efference copy and the reafference copy. If to match well, then the brain infers the action as self-generated. If they do not match, then the movement or the kind of act that is performed is inferred by the brain as generated by something which is non-self. So if I have to infer something being generated as non-self, I may say that there is some alien force which is influencing my movements, and that's how this is happening. So this is one of the classical symptoms that we see in people with schizophrenia. So this is the slide that describes what happens in schizophrenia patient with respect to the corollary discharge abnormalities. There is a mismatch which happens between the efference copy and the reafference copy, due to which the self-generated movements are inferred as generated by non-self. And corollary discharge essentially looks at the predicted model and what is the received sensory feedback. So in that sense, it relates with the predictive coding and the Bayesian brain framework of schizophrenia. I'll give one more example. Like as we keep speaking, especially in a conversational situation where we are interacting with multiple people, when I speak to somebody, I should not be paying attention to what I am speaking. Rather, I should pay attention to the response of the person who is talking to me. Here, the brain has evolved a mechanism by which the words generated by me will not elicit significant impairment. And if there are connectivities that involve fronto-temporoparietal regions, that is seen to be the basis for the generation of delusions, especially in the prefrontal parietal brain regions, and auditory hallucination, which involve the prefrontal temporal brain network abnormalities. We used functional MRI, through which we measured the resting brain connectivity in patients that have schizophrenia. And we employed an ensemble model, which we call as emphasis, that is ensemble algorithm with multiple parcellation for schizophrenia prediction. Basically, this model stacks prediction from several single source models, each based on the features of regional activity and functional connectivity. And we use different types of brain parcellation scheme. And we applied a machine learning algorithm, and this analysis yielded a classification accuracy of 87% in predicting schizophrenia. Specifically with respect to the Bayesian brain aspect, what we found out in these analyses is the differential disconnectivity in schizophrenia involved frontoparietal hypoconnectivity with auditory network hyperconnectivity. So basically, these are some of the regions which are implicated to underlie the prediction network of the brain. And this kind of prediction network abnormality is in alignment with the Bayesian brain postulate of schizophrenia. So in this part of the presentation till now, I tried to give some introductory aspects of the perception and perceptual abnormalities in schizophrenia, linked it with the Bayesian approach in terms of the constructivist view of perception, and then gave examples in terms of certain symptoms of schizophrenia like hallucinations and delusions, and how they could be linked with the Bayesian brain abnormalities. And then I gave an example of some of the functional MRI research observations from our center to give some indirect support to Bayesian brain postulate of schizophrenia. Now, in the second part of my presentation, I will give some illustrations on how some of these abnormalities can be modulated using certain neuromodulation intervention, and that is where we have a lot of collaborative potential with several facets of engineering specialities. Of course, some of the functional MRI and Bayesian modeling, there is a lot of scope for collaboration with people from mathematics expertise. And then I will also end with some of the modeling related future possibilities. Now, moving on to the second part of presentation, various symptoms of schizophrenia are postulated to have another component which is called as neuroplasticity abnormalities, in the sense like how the brain gets oneself shaped with more and more environmental exposures and stimulus experiences. Now, if you look at the neuroplasticity signaling pathways, they involve some of the neurotransmitters that I mentioned, the dopamine, GABA, and the glutamate. So essentially, the neuroplasticity abnormalities open up an avenue for modulation and modification. That is a very interesting concept, that if we apply a weak direct current, we can modulate the neuroplasticity. And this is where we got interested with a neuromodulation technique called transcranial direct current stimulation, or TDCS. TDCS is a non-invasive, safe technique that involves application of low intensity direct current in the strength of 1 to 2 milliampere range. And this current is delivered using bioconducting electrodes that are placed on the scalp. And the electrodes are placed on the scalp and by using saline soaked sponges. So the entire delivery of the neuromodulation is very tolerable and without any major discomfort. The postulate is polarity specific neuromodulation happens due to transcranial direct current stimulation. Let me illustrate this polarity specific neuromodulation. What we see here is the action potential recording from a neuron. We see a different action potential here occurring at a specific frequency. If the TDCS is given, especially at the anodal current site, what happens is the resting membrane potential of the neuron becomes more depolarized, that is, becomes less negative, so that the frequency of action potential increases. So this kind of modulation happens with a polarity specific increase in terms of the firing of the neuronal action potential rate. On the other hand, if a cathodal current is applied, the resting membrane potential becomes hyperpolarized, that is, becomes more negative, so that the occurrence of action potential can stop. So in simpler term, an anodal current is likely to increase the number of action potential, which can be equated to brain stimulation in a very simplistic term. On the other hand, a cathodal current can decrease the number of action potential, which can be equated to inhibition of the brain state in a very simplistic term. And there are studies that link with the anodal current effects with the neurotransmitter changes in GABA, and cathodal current with glutamatergic transmission. So there is a consistent body of evidence that has looked at multiple levels, that is electrophysiological as well as neurochemical studies, which give a coherent picture that anodal TDCS has an enhancing effect and a cathodal TDCS may have an inhibiting effect. In addition, this TDCS is also shown to enhance the secretion of certain neuroplasticity enhancing factors like brain-derived neurotropic factors. So put together, the TDCS can modulate brain, and through some other neurotropic and neurochemical mechanism, it can actually lead to changes in the brain, which means it can modulate neural plasticity. So this is the summary slide, which shows how an anodal TDCS can cause several downstream changes, which leads to the BDNF, that is brain-derived neurotrophic factor signaling, which can modulate the neuroplasticity. And there are also postulated role of calcium and several other molecular and cellular cascades that involve certain features like inflammation, angiogenesis, and neurogenesis in this multi-level neurobiological mechanism of TDCS. Now, with respect to schizophrenia, if you want to use TDCS, I was mentioning about the delusions and hallucinations. There are brain imaging studies that suggest these symptoms, delusions and the hallucinations, which can also be called as positive symptoms, is associated with abnormal hyperactivation of certain brain region. For instance, the temporoparietal brain region, which is indicated in the blue color here. On the other hand, the negative symptoms, which I illustrated at the beginning of the talk, that is symptoms like lack of motivation, a lack of willingness to speak, so on and so forth, is associated with reduced functioning of the prefrontal brain region. So in schizophrenia, if one has to put it in a simple way, there are certain brain regions which may be abnormally hyperexcited, and there are certain brain regions which are abnormally hypoactivated. So this gives a nice instance for us to use cathodal current to inhibit the abnormally hyperactive brain region and anodal current to enhance the hypoactive brain region. So this is the schema of the transcranial direct current stimulation treatment protocol, in which we place the cathodal electrode corresponding to the region of the temporoparietal junction. The electrode will be placed on the scalp, whereas the anodal current will be placed in the region of the scalp that corresponds to the prefrontal cortex. So in this treatment, the person that receives the treatment will be fully conscious that the electrode size of 35 centimeters square is placed on the scalp. The stimulation intensity that we give is about 2 milliampere for a duration of 20 minutes. And the typical TDCS treatment course that we give will span over 5 days. We give 2 sessions, that is 20-minute session, 3 hours gap, and then another 20 minutes session. So the person who is being treated will be fully alert and cooperative and will not have any significant discomfort during the treatment. See, we used a clinical trial design that employed a randomized double-blind sham-controlled study in which we demonstrated the true TDCS in comparison to the sham TDCS resulted in significant reduction of medication-resistant auditory hallucinations, even with about 5 days of treatment. So that was something which is very encouraging. And we have started using TDCS based on some of these rigorous research findings. This is one study that we reported from our center. There are similar studies that have been reported from other centers. To optimize the technology of TDCS, we also use what is called as a high definition TDCS, in which the electrode application is in the form of a ring configuration, so that the focality of the current application becomes much more precise. So in high definition TDCS, we place this ring electrode configuration in the scalp region corresponding to the temporoparietal junction. So this is a recent set of studies that we are doing, where we found significant improvement in hallucination, even with a refined form of TDCS, that is the high definition TDCS. In addition, we have also done some studies to look at the Bayesian brain correlates, that is the corollary discharge. If I have to put it in a simple way, if TDCS improves hallucination, and hallucinations are also linked with the corollary discharge abnormalities that involve N100. So there is a possibility after TDCS, the corollary discharge deficit underlying the hallucinations should also improve. So we could see that in a set of 2 publications. Here, this is the pre-TDCS talk condition where we find the N100 to be much deeper, whereas once we give the TDCS, the self-generated talk does not involve significant activation of the auditory cortex. And we have replicated this observation using a randomized double-blind sham-controlled design. So essentially, these findings suggest that the modulation of TDCS can help us to understand certain components of the Bayesian brain abnormalities in schizophrenia. Coming to the last part of my presentation, I would like to emphasize the points and some of the findings that I are rather selective, and they primarily focused on some of the positive findings that we got, which helped us to understand how these symptoms happen and how TDCS may modulate these symptoms. At one level, it may make certain complex disorders like schizophrenia very simple, but in this context, I always remember the profound statement by Lyle Watson, which says, if the brain were so simple we could understand it, we would be so simple we couldn't. I'll give an example. Now, in our TDCS research studies, while we see some patients who respond, there are also many who do not respond. Even though we give identical parameters, we use identical treatment protocols, and we also see people that are otherwise clinically comparable. So what we also did was we wanted to see whether the brain structure has got any influence on how the current spreads when we give TDCS. So what we see here is the comparative electrical potential gradient map, which is a simulated modeling analysis outcome in which we have simulated the likely current distribution in a patient that has received a TDCS using the MRI image of the person. What we found here on the left side in a good responder, that is in a patient who showed near total improvement in auditory hallucinations after TDCS, the peaking of the current happened in the temporoparietal junction, which is the area where we wanted the current to get focused. On the other hand, in a non-responding patient, when we simulated the likely electrical potential gradient map using the MRI image of the non-responder, we found the peaking of the current is much away from the temporoparietal junction. So essentially, this could be inferred as one of the reasons why this person did not respond, which means if we can simulate and understand the likely area of current peaking, we can perhaps place the electrodes in a different fashion, which is an individual specific or personalized fashion, so that the response to treatment may be optimized. So this is one area where there is potential for collaborative research work, where people with expertise from mathematics, technology, and clinical and neuroscience background can work together. So this is where the future of brain stimulation research, including TDCS, has the scope. When we look at various factors that could influence the neurophysiological and behavioral effects of non-invasive brain stimulation. For instance, TDCS is a non-invasive brain stimulation. There are so many factors. These are clinical factors, and there are also certain brain stimulation specific factors, and also there could be some neuroplasticity related factors like genetics of brain-derived neurotrophic factor. Also, there are brain morphology and the anatomy related influences. So what we need is a multi-level approach with people that come from different specialities working together to understand and derive causal mechanisms of how some of these brain stimulation work. And the Bayesian brain is one approach where we can have a paradigm through which all these experiments could be performed, and we can understand more about how brain functions, as well as how some of these neuromodulatory technique influence the brain. So to this effect, we have initiated a clinical research center for neuromodulation in psychiatry. This is a multi-centered research which we are doing in India, and we are seeking for collaborative links with the scientists across various specialities. In this research, we are doing translational disease modeling, and then we intend to use big data analysis, where we hope to collaborate with the people that have machine learning expertise. Through some of these research studies, we wish to move the science to society, so that the benefits of all these neuroscientific approaches can result in optimized treatment approaches. So in this context, some of the newer findings that we have published, this was a manuscript that was under review sometime before, just recently it got accepted and published, where we found TDCS to improve some of the prediction error signaling in the schizophrenia. So essentially, through some of these research attempts, we want to have a multi-level research collaboration. And one of the postulates that is interesting to examine, especially in collaboration with people from mathematics and engineering background, is the Bayesian brain modeling and how it links with schizophrenia and how it can be modulated using some of these brain stimulation techniques. So, with this, I'll stop, and I wish to acknowledge the team of scientists that work with me. We run a schizophrenia treatment program, which we call as individualized schizophrenia and treatment reintegration, which is the INSTAR program, where several of my colleagues work. We work together as the clinical side, and we also have a lot of researchers that work from the lab side, who have specialization in the computational aspects and the genetics and related analysis aspect. And we have several other investigators whom I wish to acknowledge that work with us in this program. And with this, I thank again for this opportunity, and I look forward to interacting more on this. And if there are specific questions and comments, I'm happy to interact and learn. Thank you. Thanks again.
Thank you. All right, Professor, we had some technical problem, but now everything's sorted out. So please go ahead with your questions, whatever you guys have question to put. Anyone? Yes, please.
Yes, thank you. And sorry, thank you for your presentation. Important for the patients in the end and to further our understanding of this field. Could you explain a bit how you execute the neurotargeting process, as you have shown that some of the patients have different brains than others, as we all do have. So how does the neurotargeting process look like? How do you decide on the locations for the electrodes?
Okay, yeah. Thanks. This is a very important question. The current practice involves an approximate neurotargeting, in the sense we use the EEG 1020 system to place the electrodes, but we see that there is a lot of inter-individual variation in using this kind of approximate approach. So that is where the neuro-targeting in a precise fashion is a method which can optimize this treatment. Now, that neuro-targeting can be delivered by acquiring a structural MRI image, and then we can actually use the high definition TDCS electrodes, which are rather smaller in size. And currently there are standard simulation protocols which are available with some of the existing TDCS equipments software, in which we can use these specific location and see whether the current is peaking in the intended area. But more precise way will be like we can convert the structural MRI data into by applying a finite element modeling into a mesh, and we can assign different connectivities to the gray matter, white matter, and CSF, and that will help us to solve how the likely brain electricity distribution will be for that particular individual. And if we can simulate different electrode placements in this model, that will help us to understand what will be the best electrode placement for that specific person, which will help us to result and get the optimal current peaking in the region in which we want it. For instance, for hallucination, we may want the current to peak in temporoparietal junction. So this is a research which we are doing, and mathematically, the solving the finite element modeling related challenges. I understand there is a software, something like an abacus, which helps us to do that. So I'm collaborating with some people that have expertise in this area through which this is being implemented. So the slide in which I showed the current peaking between a responder and non-responder is the preliminary observation that we have got from such a research approach. I hope this has given some information in response to the question. If you seek more clarification, I'm happy to discuss further. Thank you.
Thank you, Professor.
So we are very sorry for all online participants because we have some technical problem here, but I'm so sorry. And thank you very much for being here. And if anyone has more question, please ask. Professor Venkat is here. So it would be great. We still have 5 minutes time. So if somebody has questions, comment, anything want to talk to Professor Venkat, you can talk to him. He's a very great scientist in India, and he got a lots of awards from the government of India as well as lots of research organizations in the world, and he's expert in this field. So if anybody has interest, please send him email also, and he reply very fast in his everybody's email. I'm very happy to be connected with Professor Venkat. Yes, please go ahead. So Professor Degi Khan going to ask some questions.
Thank you. Very interesting slides. And in Korea, if we try to develop system to determine or to detect some disease like dementia or Parkinson disease, actually there are some legal problem because it is the medical doctor who has to define such a disease. So or there are some problem in the presentation, so I didn't get full context. But one of the research you use ensemble to determine the patient with schizophrenia, right? So
yeah.
I'm just wondering if in India it is okay or it's legally possible to make such a decision by the program. Thank you.
Okay, yeah, thanks for the important question. The diagnosis is still based on clinical evaluation. Now we are trying to explore additional ways, say for instance, whether we can use functional MRI to see some patterns. The findings that I showed are group level findings. Slowly we are trying to see whether we can move towards individual based finding with which we can make a diagnosis. So as of now, the application of any of these techniques like functional MRI is not a standard practice. These are still in the research domain, and we need to work more to take it to the diagnostic standards in terms of the internationally accepted diagnostic criteria. Say, for instance, ICD-10 or DSM-5. Now ICD-11 is just come. So currently they are not legally applicable in India also.
All right. Thank you, Professor. Is there any other question? Anyone? Professor Tiwari, please give some comment about today's event. And to give the thanks to Professor Venkat, I would like to say, invite you to say something about that.
No, thank you, Dr. Venkat, for such a good presentation. And I know you that many of my students have contacted you. This is a very area where the doctors, because when we work on EEG signals, and we are also working on EEG signals, detecting emotions from EEG signal, because as per theory of Ekman, the number of emotions you can see on face is very less. So you can detect facial emotions only some numbers of 7 to 8. But from EEG, you can detect many kinds of emotions. So EEG is one of the best presenter signal of brain, which can give a lot of information. So in that way, and he is working on basically modulation. Of course, there is an ethical issue about the neuromodulation, because many of the aspects of that, if you put more current in our brain, now what side effect it can have, and that requires a lot of research. Also ethical issues. So these things are there, but we have in India this NIMHANS, which is a very highly researched medical as well as many other kinds of engineers are working together. And it is a national institute. And we have also some National Brain Research Institute in Gurgaon. And all of them are collaborating. And really, these are the very important, very interdisciplinary kind of idea. And initiating such a great presentation to our community is really very good. And we hope that all of us can collaborate with him. And he is really very, very sincerely responding to everybody, as he says. So with that, I thank you a lot for being present here. And I hope that you will remain connected with all of us. Thank you very much.
Thank you. Thank you, sir.
Thank you, Professor Venkat, and thank you. Yes. Thank you, Professor Venkat, very much for accepting our invitation and giving your talk here. And we hope in future more IHCI societies, all members can connect. And I just want to mention Professor Venkat is a doctor, so I think he has a legal right to use this kind of data. As we are engineer, so we cannot do, but he can do because he has real-time data. So I just wanted to include here. So thank you very much, Professor Venkat. Thank you.
Thank you.
And now we would like to have a group photo with all online participants as well as on-site participants. So I would like to request all online participants to turn on your camera, and just we have a 1 minute photo. So you guys can turn on your camera and we can have a group photo. And also I would like to request everyone here who are attending here, all foreign professors and local all participants, please come here on the stage. We can have group photo. So we can see that the participants who are very much dedicated to IHCI conference. So it would be great pleasure for us. So please come on the stage, everyone. So we can stay here or somebody here, so people can take here, right? Yeah, I can see here Professor Mark, Professor Madhusudan, I can see now to them. Thank you so much for attending all sessions, Professor. And there are
hello, Dhananjay, can you hear me?
Yes, Professor, I can see you.
Good, good.
Lots of people are there on online site. Yeah. So they are continuously supporting us for 1 year. This